Hello everybody. So today I have another case history. It's the Transcona Silo. I'll talk to you about that first, and then we will discuss what the particles of soils are made of. So we're going to zoom in inside the particle and take them apart and see what they're made of. So let me turn up the lights and then we'll start the So the story is the Transcona Silo, which failed in 1913. These are the credits. You will see that we're going to be in Winnipeg in Canada, where the silo is located. So here's the Transcona Silo. You can see the grain storage, and the trucks come through here to be loaded with grain. The Transcona Silo weighed about 20,000 tons. So here's the construction. Now remember 1913, so this is over 100 years ago. And then here's the silo completed. You see that the hopper and the workhouse to load the trucks that go through here, and then this is the bin house where all the grain is stored. And the grain is pretty heavy, and the pressure, remember this number here, 300 kilopascal. So here is the dimensions. So this is 92 feet, about 30 meters high. So 30 meters is about a 10-story building. So this is a pretty big structure. And you see about 25 meters in width. So it's quite and here's the failure. So one day the soil couldn't take the pressure, and as the grain was loaded, the silo itself failed by rotation. So you remember the Tower of Pisa, which rotated about 5 degrees. Well, this one is rotated a lot more, but this is the same type of bearing capacity failure that we're talking about. So in the rotation, the silo pushed the soil, and so you have the soil heaving on this side, and the soil being kicked out on the other side, on that side here. So here is the final, you see the silo tilted 27 degrees or so. Remember, Pisa was 5, this was 127. What was remarkable about this failure is that the structure itself remained intact. So the people in the area decided to actually save the structure rather than tear it apart and build a new one. They actually redressed the situation, and so they calculated how much weight there was on each. They excavated under the structure and placed some jacks, some columns and jacks, so that they could jack this up and bring this one down to level the silo slowly but surely. Right, so here's the work taking place. We're on the high side of the silo, and the foundation contractor is, you can see the people working in there, and all those jacks that are actually trying to re-level that structure. And here is the structure after the fact. So it looks like new after this soil failure. This is quite rare, actually. When you have a failure of that magnitude, it's rare that we can actually save the structure. But in this case, this is what was done. So here's the type of soil that was located under the structure. You can see here stiff blue clay with very soft clay, some gravel, but clay again, clay and gravel, and then the bedrock at about elevation 718. So these are feet, so 770, 720, you've got about 15 to 20 meters of stiff clay. The clay itself is not that soft, but the pressure obviously was too much. So this is the second time in those case history that you see how important it is to calculate how much pressure the soil can take and then divide this by a factor of safety to be sure that we apply a safe pressure rather than facing some of these failure potentials. You can see here some data, some engineering properties of the soil. This is the compressive strength, and the compressive strength is equal to 2 times the undrained shear strength. So that you see about 1 ton per square foot, and 1 ton per square foot is 100 kilopascal. So if I divide this by 2 to get the undrained shear strength, I end up with about 50 kilopascal. So remember, the pressure was 300 and the undrained shear strength was 50. Here's the water content on this side. So probably around 50% on the average. That's quite high. You know, the water content in around College Station is probably more like 25% or so. And then this number at 50% was quite high. More of this type of data. We will talk soon about the Atterberg limit. You have plastic limit here, liquid limit. Here's the moisture content that I showed you. And then here is the particle size distribution in percent. That's what we've been talking about, the grain size analysis. And this was done from a sample at 10-foot depth, 15, 20, and so on. And you can see here the percent clay is about 40%. The percent silt is another 40%, with about 15% of sand and 5% of gravel. This gives you an idea. So this is definitely a fine-grained soil. A lot of the material is passing the sieve number 200 with an opening of 0.075 millimeters. And again, this is the unconfined strength, around 2,000 psf or 1 ton per square foot, which gives us half of that as the undrained shear strength, or 50 kPa. There were some consolidation tests performed. These are tests where you put a disc of soil about 25 millimeter high and 50 or 75 millimeter in diameter, and then you compress it, and you record the relationship between the pressure and the strain. It's kind of a stress-strain curve, but it's plotted in a funny way, and we'll get back on this type of soil test towards the end of the semester. So here's the something. So this was 1913, and fast forward 100 years, and 100 years ago we didn't have computers. We didn't have. I say we. I wasn't around, but there was no computers. The calculations were done by hand, and actually, geotechnical engineering was hardly born at the time, so we didn't know yet about undrained shear strength and all this. But fast forward 100 years, James Blatz, a professor at the University of Winnipeg, did some analysis to show that the factor of safety against bearing capacity failure was definitely too low. And you can see it here at 0.95. So let me bring up the light, and I wanted to do a little bit of calculations with you, because I believe this is the last slide. Yeah. Let me close this. So I wanted to do some calculations. You remember I said that the pressure, let me turn off the screen up there. Yeah. So the pressure under the silo, the pressure here was 300 kilopascal. And the soil was a clay that had an undrained shear strength equal to 50 kilopascal. And if you remember what we discussed with the Tower of Pisa, we said that the ultimate pressure that you can place on a clay, on a fine-grained soil, can be estimated by 6 times the undrained shear strength. So in this case, it would be 6 times 50 or 300 kilopascal. Okay, so the ultimate pressure is 300 kilopascal. You put 300 kilopascal of pressure, boom, you get a failure. Today, we would consider 300, and we would do P safe equals the ultimate pressure divided by a factor of safety, let's say 3, and that would give us a safe pressure of 100 kPa. We would consider the weight and say weight of 20,000 tons divided by the length times the width gives us 100. And so we would calculate the width and the length necessary for the foundation to generate only a safe pressure. So it's likely that, you know, the foundation would have to be larger than the silo itself to be able to reduce the pressure to something that would be much more manageable, say 100 kPa. So this is a type of, I mean, this is a very a simplification of the process, but this is the kind of work that geotechnical engineers do when it comes to foundation and determining how much pressure you can put on the soil. Okay, so that was the Transcona Silo case history. Let's move on to and go back to our discussion about the particles. And we're going to talk about particle composition. Particle composition. So what are the soil particles made of? You remember now we had gravel, sand, silt, and clay. And one of the first things I told you when we discussed that is that they don't have the same shape. They don't have the same shape because they're not made of the same material, although all of them are made of minerals, or at least most of them. There's some organic soils as well, but they're made mostly of minerals. And you know, the distinction between mineral and organic basically is that organic is living or has lived, like a tree is an organic material. We are organic materials. Sodium, silica are minerals, and that's the distinction. Okay? In crude terms. So particle composition, you remember that we talked about sand and gravel first. So gravel, sand, and the larger silt particles tend to be rounded. I mean, they can be angular, but overall they have the shape of a sphere, and they're made of silica primarily. So silica is SiO2. So Si has a valence of 4 plus, and O is -2, so O2 is -4, and therefore SiO2 is balanced electrically, if you wish. And so that's one of the components. We also have, let me see, I have it here. You can also have feldspar, which is another possible component. I'm not going to write the chemical composition. And mica is the other possible component of these gravel. Silica is quite stable. Mica is not as stable and can be broken down into finer particles. But these are the three main components of these gravel, sand, and larger silt particles. So as I'm zooming in on the particle, you can think of the particle as a house, and these minerals are the bricks that make up the house. So these minerals are building together to make that bigger particle. So that's, and remember that these, the forces that dominate the behavior of these particles are gravity forces. Okay, these particles, there are, electromagnetic and electrostatic forces, but they're so small compared to the weight of the particles that these particles do behave mostly by gravity, and therefore friction is a very important part of shear strength and things like this. Now when it comes to the smaller clay and smaller silt particles, that's a different story. And actually it's a much longer story because they have some, what they're made of is much more important to us than on the gravel and the sand size. So let me start by saying that there are three types of clay minerals. So let's write it here. 3 types. By the way, I'm on page 28. Right? 3 types of clay minerals. Okay? You have Keratinite, you have Halite, and you have Smectite. And within the Smectite family, you have Montmorillonite and bentonite. And as we go in this direction, we've got decreasing particle size. Okay. Now, what do I mean by particle size? How big is small, if you wish? Well, let me first say that 1 nanometer is 10 to the minus 9 meters. Okay? How big? So you have meter, you have millimeters, you have micrometers, and then you have nanometers. So very small. How big are those particles? Well, I'll start with the Keratinite, which is the big one of these three minerals. And Keratinite is, so I'll try to, so this is K-O-Nite. It's about 100 nanometer thick and about 1,000 nanometer long. Extremely small. It is coated, we'll come back to this, it is coated with a layer called a layer of absorbed water. And so this absorbed water layer coats the particle all the way around like this. And we'll see why the water is attracted to the minerals, that the Keratinite mineral. And that thickness right here is of the order of 40 nanometers. So this is about 40 nanometers. Keratinite, baby powder. Okay, it's used, so you can, it's very smooth, very smooth. You certainly, when you have baby powder in your hand, you certainly cannot feel the grit of the powder, but you certainly could feel the grit of a small sand or large silt particle if it was in your fingers. So this is the giant, and this giant is only 100 nanometers by 1,000 nanometers. Now, if I go to the Montmorillonite, for example, then the Montmorillonite, if I do it to scale, this is 100, this would be 3. And this would be, I'm trying to do it, not to scale, because obviously this is too big, but at least the relative scale of the two here. So this would be 3 nanometer. This would be about 100 nanometer. And here I'm doing the Montmorillonite particle. And it would be coated, again, by water attracted to it, and maybe 20 nanometer rather, or so of coating. So you say, who cares? Well, we do care for one reason, because you see this absorbed water here is 20 to 3. Its absorbed water is 40 to 100, so that's 40%. This one is, what is this, 600% or so, more. So if you do the analysis and you find out that you have a lot of Montmorillonite, then this material has a tremendous ability to swell. This material has a area of the order of 800 square meter per gram. 800 square meter is the size of a basketball court. Okay, so 1 gram of this material here has enough area around the particles to cover an entire basketball court. And because the water is attracted to the surface of these Montmorillonite particles, then that's the tremendous potential for swelling. So if you decide to buy a house and you see a wonderful landscape and area and then take a sample, as I did in 1988. And unfortunately, I discovered that I had some serious trouble by doing the Heidelberg limits, and we'll do that. We'll discuss that next time. But it was the right place, and I wanted it, and it was not very expensive. Maybe for that reason, I don't know. But I had to be very careful with foundation, swelling, shrinking, cracking, and all that stuff. And we'll discuss this later on in the class. But so that's why these sorts of things end up being quite important to us. So that's in terms of size. The minerals themselves are made of two types of, maybe I'll add it here on this side. And the minerals themselves are made of a sheet of silica and a sheet of gibbsite. So silica, I told you, SiO2, and the gibbsite, I don't know it by heart. Where is the gibbsite in here? Al2OH6. Al2OH6. So you don't have to know that stuff, but it's important. You do have to know the order of magnitude of the scale of those particles. So a short question on the midterm could be, what's the typical size of a Montmorillonite particle? So you say 5 by 100 or something like that. So that by itself is important. Now these two, kaolinite. So if you wish, this is the particle, and the particle itself is made of what I was talking to you about, bricks. All right, so this may be a simplification, but each of those bricks is made of a layer of silica over a layer of gibbsite. Okay? And if I go into the Montmorillon bricks, then these bricks right here are made of a layer of gibbsite sandwiched between two silica. So it looks like this: silica, gibbsite, silica. And that means that you can put water in here, water in there, but here you can only put it between those two. So this is detail, if you want, of what those bricks are going to be made of. All right, so I wanted to talk about this, then this. Now, so let's go back and make a drawing of a clay particle. So here is the clay particle. You now have an idea of the scale of that particle. And you have the bricks in there that have silica and so what happens is that if in the making of this particle, if the silica is not present, to make up the SiO2. So remember, Si is 4+. So if the silica is not available, then the particle is going to try to grab another cation. So cations are positive ions. Okay, so Si 4+ is a positive ion, so we call it a cation. We have Al3+. We have magnesium 2+. And then we have sodium 1+. Okay. NaCl, salt. So these are the cations that are kind of floating around, if you wish. And the particle is trying to get organized, and it can't find an Si4+. But it finds an Al3+ that has the same shape. You know those bricks here. Particle says, okay, fine, I'm going to grab the Al3+, stick it in there, and that's going to fit well, except that now you have an electric imbalance because you needed a 4+ to form the SiO2, and you only get the 3+, and now you form a particle that has negative charges on the surface. Okay, so that's the main reason. And this business of using or plugging a hole, if you wish, an Si4+, and you don't have Si4+, so you stick in there an Al3+. This is called isomorphous substitution. So in Greek, iso is same, morph is shape, so same shape substitution. Isomorphous is a fancy word. But that could be a question, you know, a short question, a midterm. What is isomorphous substitution? Well, it's substitution of Si4+ for a lower valence cation, maybe Al3+. Anyway, so we end up with a clay particle, which now is electrically deficient, and it forms negative charges on the surface. So because it has this negative charge, if there are some positive charges that are floating around, they're going to get on that particle and get stuck because of the magnetic attraction. And these are typically the water dipoles. So in the water, you have these ions, which are H2O, and they're typically split in H+ and OH-. So they get ionized, if you wish, and they have their own polar directions. So you can think of water as a bunch of little magnets that float between the particles, and these magnets then are attracted the plus to the minus. So then these water dipoles will start coating the particle, and in doing so, they form what is called the adsorbed water layer. So again, question, what is the adsorbed water layer? And you can imagine that the adsorbed water layer on the monomer is going to be very large compared to the thickness of the particle, compared to what would happen to the kaolinite. So kaolinite can swell, but not much. Monomer can swell a lot because of this huge area that's available. So this is the adsorbed water layer. And that's where the electrical part of these clay particles develops. And this water is not water when you open the tap. You know, this water is very strongly bound to the particle. As you get closer to the particle, the water comes from free water that can actually seep through the soil to this viscous, if you wish, viscous water that's really attached. So it would be, if you had, you know, a knife that would be so small, in nanometer, it'd be tough to scrape the water off the particle because it's so strongly bound to it. So that, let me check here. Yeah, that basically concludes what I wanted to talk about, the particle composition. I wanted to, there was one problem I wanted to do with you on the weight-volume relationship. You know, we only did one problem, I wanted to do another one. So I want to take a minute here to do that problem, which will help you to understand and hopefully help you avoid making a mistake when you handle the water content, because that's an important parameter. And then once we do that, if we have time, then we will start discussing the Atterberg limits. All right, so I'm looking at problem 3.3. Let's see, let me erase this. So this is problem 3.3. Page 37. All right, so the story is a farmer wants to buy a 10-kilogram bag of fertilizer. So he goes to the market and fertilizer. So fertilizer is organic material. So farmer wants to buy 10-kilogram bag of fertilizer. And he has the choice between two merchants. Merchant A sells the 10-kilogram bag for $10. So you can buy it from the first merchant, and the 10 kilogram for $10. And on the bag it says dry. So there's no water in the bag of fertilizer. And then the second merchant, B, says, I'll sell you the 10 kilogram bag for $8. But the farmer is smart, and he looks on the bag, and the bag says water content 20%. And the farmer is not interested in buying water. He wants to buy the dry part of the fertilizer. The question is, which one is the least expensive if you want to look at what, the cost of the dry component. So we need to look at this and find out how much. So in the first case, we have case A, and we have, so this is a phase diagram type of problem. In the first case, you have solids and air. That's merchant A. And this weighs 10 kilogram. So there's no doubt that you have 10 kilogram for $10, so it's 10 divided by 10 equals $1 per kilogram. And then in case B, then what do we have? We have solids, water, and air. We're going to put the weights on this side and the volumes on this side. So we know that the weight of water plus the weight of solids is 10 kilograms. Well, I should be doing the reasoning in mass, okay? Let me take a minute because it's critically important. Because I don't want to confuse you with mass and weight, okay? In the SI system, the unit of weight or force is 1 Newton. The unit of mass is 1 kilogram. And 1 Newton is equal to 1 kilogram accelerated, you know, F equal ma, at 1 meter per second squared. So you have to be careful because the kilonewton doesn't correspond to the kilogram. There's a ratio of 1,000 between the two. It's 1 Newton, which is 1 kilogram times 1 meter per second squared. So if I had 1 kilogram mass in my hand and I wanted to accelerate it from 0 to 1 meter per second in 1 second, then my arm would have to generate 1 Newton. And 1 Newton is about the weight of a small apple, if you want to get a sense of what that is. All right. So having said this, the kilogram may not be the best way to do this, but I wanted to be sure that you understood the distinction between the. So maybe we should. All right, let's do it right. Let's do 10, and then in the second edition, I'll change that to kilonewton. So we'll do 10 kilonewton, which is huge, by the way, because 10 kilonewton is about a ton. But at least we'll respect the. So we have $10 for 10 kilonewton, and so that's $1 per kilonewton, and that becomes very inexpensive for fertilizer. Back to this. So now we know that the weight of water plus the weight of solids, I'll write it here, weight of water plus weight of solids equal 10 kilonewton. What else do I know? Well, the bag says 20% water content, so I know that the weight of water over the weight of solids is equal to 0.2. If you might have been tempted, if I told you there is 10 kilonewton of fertilizer, the water content is 20%. How much water do I have in this material? You might have said, well, 20% of 10 is 2, so that'd be 2 kilonewton. That's wrong. Because if you did that, you would take weight of water over total weight equal water content. And that's not the definition of the water content. Water content definition is weight of water over weight of solids. So remember that. And that example allows you to do that. So then if I take those two things here, I can go back to this equation and do weight of water equals 0.2 weight of solids. So I've got 0.2 weight of solids plus weight of solids equals 10, or that's 1.2. Weight of solids equal 10 divided by 1.2, which is 8.33, I believe, kilonewton. So then, let me double check, I think that's right thing. Where are we? This page, 8.33, yeah. So then now, if you want to check the cost, remember the bag, this bag was $8. So now the cost per unit is $8 divided by 8.33. And so that's going to be less than $1. And the answer is $0.96 per kilonewton. So now, this is B, and this is A, and you're better off buying from merchant B and just drying the fertilizer if you want the dry component. Well, I don't have enough time to start at a root limit. We'll just stop here, and then I will see you next time.